Okay, welcome to lecture 8 for Calculus 1. This is going to be about the chain rule for derivatives. So suppose we wanted to calculate the derivative of a composite function or a composition of functions. This might be denoted as y is equal to f of g of x. F here is going to be the outer function. G is the inner function. So this is about a function within another function. Okay, so the definition goes, well, if y is equal to f of u is a differentiable function of u, and u is equal to g of x is a differentiable function of x, then y is equal to f of g of x is a differentiable function of x as well. Okay, so if each part of this is something we can take the derivative of, then we can go ahead and take the derivative of the composition or the combination of both of them. Okay, and here's the actual formula for the chain rule. So the derivative of f of g of x is going to be the derivative of the outer function f prime, and then we leave the inner function alone, we leave it as it was, multiplied by the derivative of the inner function g prime of x separately. Okay? In other words, y prime is the derivative of the outer function with the original inner function as the input, multiplied by the derivative of the inner function. Okay, so previously we had just been dealing with simple functions that could be differentiated with our basic rules, right? So we had functions like y is equal to x squared plus 4. You would use power rule on this. This would just go to 0 by constant rule. Y is equal to sine x. So we saw last time how that's just defined as going to be cosine x. Y prime is going to be cosine x, right? Y equals 3x plus 2. Again, power rule and your constant rule. And then y is equal to x plus tangent x. This is something you could represent this one as sine of x over cosine x, and you can go ahead and you can use your quotient rule on that. Okay, so these are all things that were simple. We didn't need chain rule. There were no composite functions or anything like that going on here. But when we start nesting these functions within each other, we're going to need chain rule. So if we took that first example and now instead of just x squared plus 4, we have that entire thing under a square root, we're going to need chain rule. If inside of your sine you had a 6x, again, you're going to need chain rule. If we took that 3x plus 2 and raised it to the fifth power, well, now you've got a function that's raised to the fifth power, not just a constant. And if you had an x squared within your tangent, same idea. Now you have a function as an input. So for all of these, we're going to need chain rule. Okay, so before we actually start diving into taking the derivative of these things, let's kind of just get trained a little bit on pulling these composite functions apart or decomposing them. Okay, so we've got some examples here. So for example, A, we're going to look at this as f of g of x. We're going to try to isolate what the inner function u is equal to g of x is, and then represent the outer function as some function of that u. Okay? So if you had, for part A, y is equal to 1 over x minus 1, that denominator is what I'm going to represent as u. That's my x minus 1. That is a function in itself. That function is falling within this outer function, which is dividing 1 by something. So this is 1 divided by u. Okay, so all we really ended up doing is replacing that denominator with u. And you could also have represented this as u to the negative 1, for example. Okay, so that negative 1 would be the outer function. In B, we've got cosine of 2x. Y is equal to cosine of 2x. Inside those parentheses, that u is going to be 2x. The outer function will just be cosine of u. Example C, you've got the square root of this polynomial, 3x squared plus x minus 2. We make that polynomial u. The outer function just becomes the square root, so y can be represented as the square root of u. And finally, y is equal to sine of x, the whole thing squared. Inside the square, u is equal to sine x. The outer function is just the square. Y is equal to u squared. All right, so let's see how this is going to work in an actual example. So suppose we wanted to find an equation for the tangent line to the curve. Y is equal to the square root of e to the x plus 3 at the point x equals 0. So this is nothing different than what we've been doing before. We already know how to find the equation for a tangent line. But this time, the function that we have to derive is a composite function, and we're going to have to use chain rule. So let's start by doing that. Let's start by finding y prime. Our first step is going to be to decompose y. So let's identify the outer function, that's the square root. We identify the inner function here in yellow, e to the x plus 3. We can represent this. Any radicals we can always represent as powers. I think that'll be a lot easier to deal with in general. So we go ahead and we represent this as e to the x plus 3, all of it raised to the 1/2 power. Now, let's take this piece by piece. The outer function, f, in red, is just u to the 1/2. So this is f of u being e to the x plus 3. We derive the outer function first and leave the u alone. We're just going to pretend u is a constant in this case, or as if it were just an x, I should say. So we're just going to pretend u is just some variable like x. We're going to ignore the fact that's equal to e to the x plus 3. So f prime of u, if we do power rule on this, 1/2 u to the negative 1/2. And we just leave it as that for now. Now, I've got a separate function. U is equal to e to the x plus 3. We take the derivative of that. Derivative of e to the x is itself. It's a special function that we talked about earlier. Derivative of e to the x is just e to the x. That 3 vanishes as we take the derivative. It becomes 0. And now let's put this together piece by piece. Okay, so y prime in general is going to be f prime of u times u prime, as our original definition was showing. So now let's put in everything in terms of u. F prime of u is 1/2 u to the negative 1/2. U prime stays as is. And now on our last line, let's put in everything back in terms of x. So for u, I'm going to substitute in e to the x plus 3. That was our definition of u. And u prime is e to the x. Okay, so we're just multiplying these. We can just rewrite that with the e to the x up front. Make this a little bit more neat. So 1/2 e to the x times e to the x plus 3, all of it raised to negative 1/2. That's your answer by chain rule. Okay, so that was our first step in finding the equation of the tangent line. We are going to have to find the slope next. So we're going to evaluate y prime at our given x value, which is 0. Okay, so we just go ahead, we plug in 0 for x into here. So 1/2 e to the 0 times e to the 0 plus 3 raised to negative 1/2. E to the 0, any constant to 0 other than 0 is of course going to be 1. So we get 4 on the inside, 1/2, 4 to the negative 1/2, which is the same thing as 1/2 times 4, 1 over 4 to the 1/2. 4 to the 1/2 is just the square root of 4, right? So it's just really 1/2 times 1/2. And we get 1/4 for our slope. Okay. So if we're going to put this into point slope form, we need y1 as well, in addition to m. X was given to us, x1 I should say. So to find y1, we just plug in our x value into the original function. X being 0, so y of 0 is equal to the square root of e to the 0 plus 3. square root of 4, which is just 2. Okay. So we've got our point slope form here. We're just going to plug in our individual elements in for each of the variables. And so we would get y minus 2 is equal to 1/4 times x minus 0 in point slope form. Or if you like, you can go ahead and rearrange this into slope-intercept form, and you get y is equal to 1/4 x plus 2. All right, let's look at our next example. So this one says, if the function s of t is equal to 1 over t squared plus 1 cubed represents the position function in meters of a particle moving horizontally, find the particle's instantaneous velocity at t equals 1 second. Okay. So to start off, we can decompose this function s of t. All right, so we just need to find its derivative and then plug in or evaluate this at t equals 1. So if we're going to decompose this function, we can rewrite, first of all, the 1 over t squared plus 1 cubed as just t squared plus 1 to the negative third power. In red, we've got our outer function, which is raising it to the negative third power, it's the exponent. The inner function being t squared plus 1. Okay? So the outer function, if we replace that t squared plus 1 as just u, the outer function is simply u to the negative 3. And then f prime of u is going to be, by power rule, we bring down the negative 3, u to the negative 4. Subtract 1 from that exponent. U again is t squared plus 1. To derive that, u prime is simply just going to be 2t. And then we're going to put this back together in our chain rule fashion. So s prime of t is equal to f prime of u times u prime. F prime of u is negative 3 u to negative 4. U prime, let's leave this as it is for a second. And in the next line, we'll make this 2t. Okay, so now in this line, we put everything in terms of t. Negative 3 t squared plus 1 to negative 4 times 2t. And then just simply combine like terms. We can move that t out front. We get negative 6t times t squared plus 1, all of it to the negative 4th power. And finally, we just have to evaluate this at t equals 1 second. Okay, so this is an instantaneous velocity function. S prime of 1 is going to be equal to 6 times 1 times 1 squared plus 1, all of it raised to negative 4. So that's going to simplify to negative 3 over 8. And because they had given us this position function in meters, the instantaneous velocity is going to be measured in meters per second. Okay. Let's see our next example. Let y equals sine to the 4th of x, or sine of x raised to the 4th power. Find y prime. Okay. So you can see I've rewritten this as sine of x inside, the quantity on the outside raised to the 4th power. So u to the 4th is our f of u being sine x. When we derive the outside, we're going to get 4u to the 3rd power by power rule. Derivative of u is just going to be cosine of x by our derivative rules definition that we saw. Put it together. So now we've got f prime, we've got u prime. Let's put them together. So y prime is equal to f prime of u times u prime, 4u to the 3rd power times u prime. Now we put everything in terms of x. U is sine of x, u prime is cosine of x. And that's it. So our derivative is 4 sine of x cubed cosine x. Okay. Now in B, let's see what happens when we reverse the order, okay? So we had sine of x as the inner function here. The fourth power was the outer function. Here, raising it to the fourth power is the inner function, and sine is now the outer function. Okay, so let's just demonstrate or see what happens, and if this is going to lead us to the same result or a different result. Okay, so we decompose our function again. Y is equal to sine of x to the fourth power. Just like we said, x to the fourth power is going to be that u, okay? So f prime of u is just going to be cosine of u, as derivative of sine is cosine. On the inside, we're going to use our power rule, 4x cubed. Let's put it together. We're going to have cosine of u times u prime. Substitute everything in terms of x now. Cosine of x to the fourth times 4x cubed. Okay, so this is leading us to a different result. So now we've got 4x cubed cosine of x to the fourth. Here we had 4 sine cubed of x cosine of x. Okay, so this is just to demonstrate that the order does matter. So what your f of x and your g of x are will change how the function's derivative is going to come out. Okay, so we just have to be careful that we make sure we're identifying the correct inner function and the correct outer function as we do these. Okay, example 5. So this one is actually going to be slightly more complicated because if you notice, we've got cube root of sine of e to the x. We've actually got 3 different functions going on here. We've got the cube root in red, we've got sine in yellow, and then we've got e to the x in pink. Okay, so there's 3 functions on x happening here. So that's fine. Let's call everything underneath the cube root u for a second. Our outermost function is just going to be f of u, which is the cube root of u. And the cube root of u we can represent as u to the 1/3 power. If it's u to the 1/3 power, we derive this by power rule. The 1/3 comes down. 1/3 minus 1, or 3/3, results in -2/3. Okay, so that's the outermost function. Now let's look at the next level. I'm going to say this is sine of v. So that e to the x, we're going to call that v for a second. Let's just pretend it's just a single variable. We'll look at that separately in the next line. But for now, u is equal to sine of v. Therefore, u prime is just going to be cosine of v. That's it. Okay. So now, in our third line, we consider v as e to the x, meaning v prime, the derivative of v, is just going to be e to the x, as the derivative of e to the x is itself. Okay, so we had this composition of 3 functions, and we wrote out each layer by itself, and we took the derivative of each layer by itself. That's the strategy. That's the way to do this. And now let's put them together piece by piece. So y prime is going to be f prime of u times u prime, and you could have written this as, if you really want to, u prime of v. Same idea. So we're leaving v in there as it was. We're not changing that. And then times v prime. Okay. So now all I'm doing is I'm putting f prime of u in terms of u. So I've got 1/3 u to -2/3. Leave these two the same for a second. Now let's put everything in terms of v. That's our next layer. So well, I've got u here, but u is just defined as sine of v. U prime is cosine of v. And v prime as well, it's already in terms of v. So we leave it for a second. And then our last step, or second to last step, I guess, before simplification, put everything in terms of x. Well, v is just e to the x, so that's going here as e to the x, going here as e to the x, and v prime is also e to the x. Okay, so this is how you're going to derive something with which is a composition of 3 functions, and the same strategy would work if you had more functions. So if you had 4 functions, you could define a new letter, or new, if you had, say, e to the w, some other function here, you could say w is some function of x, and we'd do the same thing. Okay, so you just go layer by layer. So we just clean this up a little bit. We put our e to the x up front with our 1/3. So you get 1/3 e to the x cosine of e to the x sine of e to the x to the negative 2/3. All right. And that's it. That's the strategy. So chain rule is going to be applying to a function within another function. It'll apply to multiple functions within a function. You can always just keep defining your layers and your functions and putting them together like this. All right. Well, if you like this video, please hit the like button and make sure to subscribe for more content like this. Thank you for watching.